Well, if I was given more time to do this, and before I knew about Angr or the technologies that we're going to go through this week, just based on our previous 7 weeks that we spent together, there's 50 equations. I would say maybe go automated with this. I mean, I know IDA Python, I know Ghidra and automation with Ghidra, but Ghidra doesn't have dynamic analysis, so do I want to give that up? So I'd probably go to IDA. Um, I would want to use a decompiler because the decompiler is actually pretty clean with Ghidra, so that was kind of nice. That was just like from 10-minute assessment there. I would say, okay, well maybe I'd want to do I'd want to use a decompiler, but then I'd also want to use dynamic analysis to like record all the equations. So just a rough estimate, I would think maybe bust out IDA's decompiler and doing dynamic analysis with that. But ultimately, the dynamic analysis isn't going to solve the equations, so I would say using some Python to comb through those 50 functions and translate them into equations, which then, I don't know, I'd boot up like MATLAB or something and be like, okay, and then I'd be like Wikipediaing, like, how do I solve a matrix of equations? And like, it would take me a long time to figure this out. And this problem is not an isolated special problem. What we're gonna see is that the technologies that were used to basically make this problem trivial can be applied to a wide range of cases. There are also a lot of cases that basically just totally destroy Angr and its technology and can't be used. And we're going to go over those too, so we know which tool to use when. So let me talk a little bit about this solution here. And then we're going to go over high level, what are the technologies being used? How does it work? And then we're going to kind of explore a little bit more with the API, familiarize ourselves with it, and then we're going to start applying the API. And that's just today. So not too much theory stuff, but with all of the literature that I've seen out there, or I should say a lot of literature I've seen out there, it abstracts so much away from Angr that it actually uses the word magic. Has anyone seen that in an Angr tutorial before? It says Angr does its magic or something like that. But that kind of like gets under my skin a little bit because as reverse engineers, we don't ever say, hey, trust me, just don't worry about it. You're like, no, I will worry about it. Show me the bit. And I want to know what order the bit is and what orientation it is. And, I want to know everything. So what I want to do today in this next section is we're going to go over how does it work, and then that's going to help actually feed into practical strategies to use the tool, not let Angr do its magic. Okay, so let me walk through this a little bit. So at the top here, import Angr. Then here, I'm gonna skip this stuff right here, this character and these addresses. So let me skip these things. So I'm gonna go logically through it. The first thing it does is it just bootstraps a project, and this should be very familiar syntax, just like Pwn tools, right? You just like start a project. Now you can send things, receive things, start a process, start a project. Then what it's going to do is it has something called a factory, which if you know from like object-oriented programming, it's just something that constructs objects for you. And it does a little bit of that background lifting of like initialization. If you recall from Ghidra, that was actually pretty painful a lot. Once you started dipping into the Java API and you had to like make all the objects yourself, you're not going to face that here. Okay, so Angr is actually pretty pleasant to work with. It's also well documented. So it has the strengths of Ghidra, but also the strength of the nice, easier to use syntax of IDA once you know how to use it. So you're going to create a blank state. You're going to tell the program, hey, I want you to start at this start address. And that's part of one of these constants up here. So this is something that was pulled out of the program manually. This was not automated. So it starts up a blank state. Then it's going to add an optimization, an option, a constraint. And a lot of working with Angr and solving systems of equations and things like that is about adding constraints and trimming out search space, which we're going to get into. So that's what's this here. And then next up, it's going to assign things called bit vectors for Angr. Now, bit vectors is something that kind of sounds complicated, but you've actually been dealing with bit vectors a lot. That's what registers are. So a register, if you have all Fs in a register and you add one to it, it doesn't like, add another digit, right? You just have a constrained space. It's just going to roll over. So you can actually have overflows. So that's what a bit vector is. It's just like an array of bits that could do counting and has the rules of like overflows. So we're going to look for where the input's coming in and say, hey, that's a bit vector, Angr. That's going to be a variable. And then here, moving on from this here, is you're going to start a simulation manager. Here's using factory again. And we kick off the simulation manager. You can think of it like an emulator. It's like Ghidra's emulator, or if you've used Unicorn engine as an emulator, or Kimu as an emulator, right? So that's what this is doing. Simulation manager is like an emulator. And then what you're going to do is you're going to say, hey, when you're emulating this process here, I want you to look for this address but avoid this other address. So as it's emulating and it sees a branch going one way, it says, oh, don't go that way. Go the other way. Now, this we're abstracting a lot. We're going to dig into this. And then after that, you go to your simulation manager and you say, okay, now that you have reached a certain point in the program, can you just show me what those bit vectors are? Those ones that you said, hey, those are going to represent my input. Now that you've added constraints and such, just show me what you got once you've done running your explore algorithm of like running through all this emulated state. And at that point, then this just evaluates here the cast 2 bytes. So you can remove this and it will just give you back like the numbers instead of this here. So as far as I would say Angr scripts can be very concise, and they can appear to be simple as we've just sort of gone through here. But what we're going to be going through this course is, why would you use this address? Or why would you add on this here? Or how did I choose this size bit vector? Why do I want to avoid this address but find this address? So throughout this course, we're going to dig into how do you make these choices for this program that we've seen right here, so that you can actually run through a program and explore all the different pathways of a program, and then be able to finally get out, well, if the bit vector equals this and it emulates the program, it would reach the state of find address here. And find address was another one that was pulled out manually by the reverse engineer. Okay, so right now, just the very beginning of warm and fuzzy, so let's keep it going. Okay, so let's talk about, let's give a little sense of what Angr is. At its core, and this is like their words, the authors of Angr words, it's an emulator. So just like Kimu is an emulator, it simulates an environment, and with each instruction, it can watch, because it's a simulator or an emulator, it can step by step each part of the program, and at each step you can read and write memory. So you can hook functions, you can modify functions, do things like that. It's this part of the emulation which is what is the strength. And by emulating a program and watching how variables are manipulated, what you could do is you can translate a program into another form. One of those forms is an abstract syntax tree. And then what you could do is you can run algorithms, optimization algorithms over that abstract syntax tree to then understand what are the constraints of that program. So if we think about this here, this program is expressed as a process. It's like step 1, step 2, step 3, step 4. There's even branching. Like, it's not even just a series of steps. There's possibilities here. We don't know which series of steps. This is a compressed representation of a series of many, many different possible steps. But what's the insight that we saw almost immediately as we were going through this? As we said, oh, okay, I understand this is a process, but really at its core, it's a relationship between variables. And it doesn't really matter if I check this relationship first or I check, this function. The relationships stand, and they stand apart from time. There's no ordering here that matters. If you could extract from this program, which is really messy, it has input coming from a keyboard and it has a series of steps and it has conditionals. If you could extract from it the essence of the relationships, you could use tools from mathematics to solve the inputs and outputs of those relationships. And that's what Angr does at its core, is that it facilitates the extraction of those relationships so they exist outside of time, but rather in an equation. An equation we don't usually think of as having steps other than maybe order of operations. But usually it's not as in depth of like, a million operations that have lots and lots of different possibilities based on what the input is. It's not really like that. It's just a series of equations or relationships. So that is what Angr will do at a high level. And now we're going to go in and we're going to iterate a little bit further, understand a little bit more detail, and keep going. So strength here, lots of code condensed into a small statement and solved, which is what we just demonstrated. And then its weakness here is branching, or sometimes it's called the path explosion problem. And we're going to see an example of that. So when I talked about a program being a process, every time there's an if statement and you go true or false, those are two different possibilities that those programs can be, two different sets of relationships that you can have. Now, if those if statements contain another if statement, those two possibilities now became four. And with every conditional, you can possibly have this set of constraints or this set of constraints. So there's really nothing you can do here to say what side is which. This is an equation with 1, 2, 3, 4, 5 variables. And so for you math nerds out there, which I guess that's all of us now, right? What this is this is a system of linear equations. So it's like a matrix, and you basically have to solve this. You go to each one of these is just another statement of a linear equation. And so we have something like 48 variables, and how many functions do we have? I don't know. It's quite a bit of them though. Well, I guess you can count them by the line numbers. So that's 16, and then that's 66. So we have 50 equations, and who knows how many variables. So can you solve this? You absolutely can. We could sit here and take the rest of the day and write down each equation and then solve it and things like that. So now what we're going to do is I'd like to show you a demo of Angr solving it. Now, you have the original solutions file from somebody who played for West Point, actually. Their CTF team, which Evan and I proudly trained the year before they did this. I don't think we trained them on Angr though, so I can't even come close to that one. But Bits for Everyone, that's the United States Military Academy here. Now, this is a very, I would consider this this is a somewhat complex Angr script. So what I've done here is I have a simplified version that's going to be easier for us to access and discuss. And what I want to do is I want to show you a demo of it. So here I am in introduction. I have my Angry kernel. Do my exercise setup for demo 1. And then I can run it here. Right, so that's what we're expecting. Now what I'll do is let me paste in this code. So here's the credit and the URL and everything. And then basically we went through here and kind of like simplified it a little bit more. So let me get right to the punchline here, and then we'll kind of step through it a little bit. And so let me just run this. There's the import Angr at the top. And then there's our flag. That would have been a very, very long time for us to do manually. Let me drop this in the channel, and we can walk through this simplified solution together. Go ahead and you can just drop that into your Jupyter notebook with your Angry kernel, and we can make sure that this actually is the correct one. Let's see here. There we go. So here's the command that I used in Jupyter Notebook. I just typed out the name. I was getting issues with, there's a lot of layers of interpretation here between special characters in Jupyter, special characters in the shell. So I just ran the program, and then I passed it the string. And this string is not, it's not like in this Python anywhere. It's not like hiding anywhere. This program solved those system of equations to get out that that value for our array of up to 72. And how long is this thing here? It's not short. Yeah, 51 variables you'd have to solve for, and we had 50 equations. And there was some additional hint because this was a CTF put on by Google, and at the time all of the flags were preceded by CTF brace and a closing brace. So in actuality there was more like 51 minus the 5. So 40, there was more like 46 variables that you had to solve for there. Give me a thumbs up in the channel if you got this working correctly. Could you get the password spit out, and could you run it and activate your product there? This demo should instill in you the purpose of solving Angr. You can imagine all of the weeks of training we've done so far. See, so here's some of the components here. Now, let me spend just 5 seconds on this. There are lots and lots of resources for Angr. I would like you to use the resources in this order. And they are based on like details. So like the very first one here, if you have questions, you just go to angr.io. Okay, so this is like the beginning, how to use it, blah, 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 things like that. Then you have the docs. The docs are really good. They have like an entire notebook, which we're going to, or not, they don't, it's not actually a notebook, but it might as well be. I translated it to it. So you go here. Then after that, you're going to go to the API. Then you're going to go to the source code. Then you're going to go to their systemization of knowledge paper. And then you can go to like books and research papers, and then a survey of symbolic techniques. But you definitely don't want to start here, because as fascinating as it is, it's just going to take you some time. So use it in this. It is a good paper. I'm just saying, like, go from start at 1. Do not find me. Don't let me find you crawling around the Angr source code if you haven't looked at the docs yet, because they'll save you a lot of time. Okay. All right. Now, let's do some fun stuff, right? Let's actually execute something. Okay, so let's see here. Binary, let's go to, you don't have RE6 and RE6 PowerPC. So let's do demo, demos, demo1, demo1.exe. Okay. Go ahead and set your binary to that. Okay. So we're just going to hex dump the first 20 bytes there. And now, let's see. So the very first part, and actually, you know what I'm going to do? I'm going to grab this and put it on the side because I'm going to reference it. I'm not touching anything. Okay. For those of you joining us for the first time, that's the print screen button. It should give you the ability to just take screenshots like that. Okay. So first thing, let's go from binary to assembly. Let's give this one a try. There we go. Because generating constraints, relationships of code and variables, because it is so influenced by changes in control flow, branches, you know, that decides what's actually going to be executed and what's not. If you think about if that being so influential and a series of instructions just being like, you know, it's just more explicit, but the series of instructions, there's only one output. It's not probabilistic. It's just like move, add, sub, add, push, pop, move, sub, add, right? Like all of that can be changed into a single relationship. And so the primary primitive of Angr is the basic block. And a basic block is defined as anything that doesn't have a change in control flow. So unlike IDA and Ghidra, which only changes basic blocks based on jumps, branches, things like that, but not on calls, Angr does break them on calls because you don't know what's going to happen when you jump to a call and jump back. Maybe you don't even come back. So that's why here, when you load a project, how we're going to look at assembly is we're going to use the factory and we're going to get a block here. Okay. And so this is like the centerpiece of Angr is the project. And you can see here we reference p.entry. So if you go make another cell here, you do p.entry, you can see there's the entry there. And this is actually a good time to bring up monkey patch. So if you do p.entry here, this is in decimal. Now what I'm going to do is I'm going to add comma monkey hex, excuse me, here. I'm going to run this again. Isn't that so much nicer? That's what we wanted. So that's by adding monkey hex in. So whenever you import Angr, just import monkey hex too, and it will patch over the default display and put everything in hex for you. Okay. So this is translated to assembly. Now the next thing we're going to do is let's take a look at it as its own process. And here, very simple, through the project interface here, you can look at all of the things that are loaded. So this is not just the static binary on disk anymore. This is a fully loaded object in memory. And that means you get to access things like libc. You get to access things like from the kernel. I mean, you have registers. I mean, there's a lot to access here besides just it being on disk. So even though it's not quite dynamic analysis in the sense of like you're running it on hardware, it's emulated. So you have access to all those other things you would think in a process. Okay. Next thing we'll take a look at here is Vex intermediate representation. And here, we're going to first show it with the PyVex library. and arch info. So you can go ahead and just run this. And this is what vex IR looks like. So this is specifically for the ret instruction, which is bytecode C3. And we do pyvex.lift. So this is here going us from process to, but it's really just assembly code. But you're going to the intermediate representation, and this is what it looks like. It looks real funky, just like P code does. You know, P code is like super explicit about every single thing that's happening. It's verbose and explicit. Well, that's exactly what this is here too. If you want to know what ret does, this tells you. Get the RSP register, store that into temp 0. Then you're going to take, temp 0, put it into T1. Let's see, you're going to add 8 bytes because it's a 64-bit architecture. So you're going to add 8 bytes to RSP. Let's see, you're going to put T2 into RSP. Then you're going to subtract 80. I don't know where that comes from there, but so this is what Angr is really using in the background to do all of its analysis so that it doesn't have to write different modules for every different assembly language. It gets to do it all in Vex. Now, we don't really have to touch Vex. We're going to use Angr as an abstraction for it. But it's there. It's just another intermediate language. It's got its own system of rules. Nothing paradoxical about it. Okay? So let's do the same thing here that we just did here, except now a Vex code. And this is for the binary, whereas the last one, it was for just a single instruction, the ret instruction. Here, we're going to use the project, Angr project again, like this. And then we're going to get a block, which is the basic block. Where are we going to get the basic block? Well, we're going to get at the entry. And then what form do we want it in? We want it in Vex. And then we can, PP is pretty print it. So here is the entry block of this code. So let's see if we can find the entry here in Ghidra. I don't believe there actually is an entry function here. Oh, there is. All right, there we go. All right. So let's put these side by side. Okay. So let's see. Here we have 40729, and there it is, 40729. So they match up together. So Ghidra's entry point was the same as Angr's entry point. And then here's Ghidra's P code of what's happening here. And then there is Angr's Vex, you're using pyvex code of how it's translated it. And instead of getting Vex, I think we can just cut off Vex here. And we can go right back to assembly code. Yeah, so assembly is just the default of a block. But if you don't want to see it in a block of code, like there, right? XOR, move, so those all match up. If you want to do it rather see it in Vex, just .vex, like that. And then because we're in Jupyter, it's got a pretty nice class explorer. So here, if I take this, and I just put this in a new cell, you can do dot and then tab complete, and it should open for us. Let me try this. There we go. So we looked at Vex. Where is Vex? Angr project.binary. Interesting. Oh, I don't see it there. Okay, well, we'll come back to it. So we can also do dir like this. Project.factory block project entry, like that. and we can get all the things that are available. Yeah, so there's vex there, arch, you know. Okay. All right. So that's that's sort of like the stuff that we are familiar with already just from Ghidra, from IDA. Binary goes to assembly, assembly goes to process, process goes to intermediate representation. Now we're going to get into this stuff that is kind of new to us, which is, what is it? What do you mean by symbolic equation? It's kind of nebulous, right? Let me open up. Let's see here. It's way too big. Okay. So here I am saying, in general, a symbolic equation. Now, this is a very general title. Symbolic equation can mean a lot of different things. It can mean a system of linear equations, like a matrix. It could take in a form of like a graph, because you can write a graph as a matrix. You can have special kinds of trees that are basically like graphs, like nodes and links. And you can have sometimes compilers. You might have heard of a syntax tree of like, if you have a statement, how do you parse a statement for orders of operations? And then sometimes a common one to use is called abstract syntax tree. And Angr has its own built-in library called Clarify, which will take code from Vex and then generate abstract syntax trees, which is just a way to represent a program as a tree. Now we're gonna dig into this a little bit more, but here's the best way I know how to do this is, instead of going all the way down step by step, which we did binary, assembly, process, vex. What I'm going to do now is I'm going to start at the next place that is familiar, which is mathematics, which is like, you know, here, constraints and concrete values, because we understand, like, you know, y equals x plus 2. You put in x equals 2, then it's 2 plus 2 is 4, you know. So that's pretty straightforward. It's this here that I think we have the least prior experience, which is how to translate a program into an equation. So that's sort of a weird thing. So we're going to talk a little bit about constraints and concrete values, and then with this being familiar, with all this being familiar, you'll see how these connect together. I have been talking for a most unusually long time for these types of classes. So let me just pause for a moment and let me take questions, discussion, anything you got. You got to have questions, because I was literally waving my hands as I was explaining things. Who's that dark figure walking behind me?
Everybody.
You know what? I'm not going to repeat that, but I'm sorry to say that it's been recorded. No questions about anything.